Welcome to the second Organic Chemistry No Frills podcast, or what I like to call Dr. Brian Lloyd's Scribblecast. Now, last lecture we learned that for any given shell, you get a series of subshells. And those subshells are ranked according to energy, S being lowest, P, then D, F, G, H, I. And so for any given shell, say n equals 3, you get a certain number of subshells. In the n equals 3 case, you get 3 subshells, the lowest energy of which is 3s, followed by 3p, followed by 3d. Now, if we're going to try to apply this to an element of the periodic table, we need a series of rules or principles that will allow us to understand how to fill electrons around the nucleus of an atom to produce a neutral element. And the first principle we want to consider is called the Aufbau Principle. So the Aufbau Principle states that electrons occupy orbitals of lowest energy first, or that is, if we are trying to produce the electron configuration of a neutral element, we start filling up the orbitals around a bare nucleus by adding the electrons to that bare nucleus and occupying orbitals that are the lowest energy, and then increase in energy. That means we require the energy ranking of all of the orbitals for every shell. And if we remember, we could write down the shells and the subshells. And if you remember, we had n equals 1 could give you a single subshell, the 1s. N equals 2 could give us 2 subshells, the 2s and 2p. N equals 3 could give us 3 subshells, the 3s, 3p, 3d. The n equals 4 shell could be split into 4 subshells, 4s, 4p, 4d, and 4f. N equals 5 subshells, 5s, 5p, 5d, 5f, and so on, 5g, and then we had the 6s and 6p, and so on. Now here's the question. Is the energy ranking, we learned last lecture that if you picked a shell, the energy ranking is S is lower than P, and P is lower than D. But if you try to create it for all the shells, is the 1s always lower than all of the 2s, or the 2s always lower than all of the 3s? How do you get the energy rankings that you can use for a neutral atom, a neutral element of the periodic table? Well, the trick we can apply is if we've written down our subshells in this pattern, all we have to do is draw diagonal arrows through our diagram. Thusly. And so on. Okay, now I'll just stop there. So let's pick an element of the periodic table. Suppose I'm interested in drawing the electronic configuration for nitrogen 7. Nitrogen has an atomic number of 7, which we recall means that nitrogen has 7 protons. In order to be neutral, I must add 7 electrons to the bare nucleus. Where do I put those electrons? Well, all I have to do is follow the diagonals to get my order. The first diagonal hits the 1s. The next diagonal hits the 2s. The next diagonal hits the 2p, and then the 3s. And I can go on. So let's go on. 3s. The next diagonal hits the 3p. Then the 4s. Followed by the 3d. Now here it gets interesting. We notice that our energy ranking places a 3d at higher energy than a 4s. So the order is not as simple as it would seem. Do I need all these subshells to create the electronic configuration for nitrogen 7? Well, in actual fact, I only need enough subshells to put in 7 electrons. How do I fill my electrons in my subshell? Well, we learned last lecture that opposites attract, and 2's company, 3's a crowd. In other words, each orbital can only hold 2 electrons, right? And they must be of opposite spin. This is actually called the Pauli Exclusion Principle. The Pauli Exclusion Principle states that only two electrons may occupy the same orbital. Now you can have less. You can have 1 electron in an orbital, but never more than 2. And the spins must be opposite spin. Now we learned that we represent the electron as an arrow, and the way arrow points represent spins. But in our electronic configuration, we don't have to worry about that. So if I apply these 2 principles to our energy ranking now, I can begin filling these with the appropriate number of electrons. And I have to remember how many orbitals each subshell has. We learned that S subshells only have 1 orbital. And 1 orbital can only hold 2 electrons in opposite spin. Well, spin's not important here, but number of electrons is. And so S can only hold 2. So the 1s can have 2 electrons, the 2s can hold 2 electrons. How many orbitals in a p? Remember, p had 3 orbitals. Each orbital can hold 2 electrons, so the p could hold 6. So I could write 6 here. But do I need 6? 2, 4, and 6 would make 10. I only need 7. So if I 2 here, that makes 4. How many electrons do I need to put in my p? 3. And so I didn't have to write these other subshells. Didn't have to write them at all. And this is my electronic configuration for nitrogen. An electronic configuration. All right, let's try using this. And I'm going to erase the Aufbau principle now. I want to do iron 26. Okay, I draw this pattern again, this pattern you see right here, and I start writing my energy levels. The first one's the 1s, followed by the 2s, and then I've got to get the 2p, 3s. I'm just following these diagonals, that one first, then that one, 2p, 3s. Next one hits 3p, 4s. And then I hit the 3D. And I can go more. 3D, 4P, 5S. That's probably enough. I only have to put in 26 electrons. I'd go further if there were more. I start filling my electrons. Remember, S only has 1 orbital, so the S's can only hold 2. 2 electrons, 2 electrons. P's have 3 orbitals. How many electrons? 6. Each orbital can hold 2. 2. 6, 2. D, how many can D hold? Well, D can hold 10 electrons because the D's have 5 orbitals. Each orbital can hold 2. Now, if I add this up, I get 2, 4, 10, 12, 18, 20, 30. Oops, I only needed 26. So this added up to 10, 20. So the D's, the remaining 6 that I need, so I can rub those out. And there is the electron configuration for iron. Okay, iron 26. Now remember, these electron configurations using this energy arrangement pattern are those typical of neutral elements. Okay, so we're not going to look at cations and anions. We'll leave that to your general chemistry course. All right. This arrangement will give you the usual or typical energy ranking for most of the elements. But there are some exceptions that occur, and we're going to consider those now. Just in case we have to go a little further, let's expand our ranking. Let's put a 6p here. and the 7s here. And so this red one would have extended down here. Okay, the elemental symbol for gold is AU. Now, look up gold in your periodic table and find its atomic number. Gold has an atomic number of 79. What does that mean? That means gold has 79 protons or 79 positive charges. In order to be a neutral atom, it must have 79 electrons. So we must draw the energy ranking for enough subshells to put in 79 electrons. So let's start. Well, there's the 1s, of course, our 2s, 2p. I'm just following the diagonals. Okay, 3s, 3p, 4s, 3d. Very good. 4p, 5s. 4p, 5s. Okay, so we did 3d, 4p, 5s. We're now on 4d. 4d, 5p, 6s, and then we jump all the way back to this diagonal and we hit 4f, 5d. For S, 5d. Let's try filling our electrons and see if we've gone far enough. S can hold 2, S can hold 2, P can hold 6, S can hold 2, P can hold 6, S can hold 2. How many can D hold? Remember, S has 1 orbital, P's have 3 orbitals, D have 5 orbitals. Each can hold 2 electrons, 10 electrons. P6, S2, another D, D10, better 0. P6, S2, F. F comes after D. So S is 1 orbital, P 3 orbitals, D 5 orbitals, F 7 orbitals, 2 electrons each. That's 14 electrons. And D can hold 10. What's that add up to? 2, 4, 10, 12, 18, 20, 30, 38, 48, 54, 56, 60, 70. We only need 9 electrons. All right. There is our predicted electronic configuration for gold. Now this is electronic configuration that gold would have in its neutral state. This is what our pattern suggests is the lowest energy state that gold can get its electrons to. Now I said this pattern works usually, but there are some exceptions. It turns out in some cases, there are situations where if you can get a filled D subshell, the D when it's filled will actually drop to lower energy than the S. Now I'm not going to change the order because it gets confusing. So it will look like I'm promoting an electron, but really I'm not. The D actually, because it gets filled, drops to lower energy. And so the alternative configuration that's possible here is a rare scenario where 1 electron from the S we've put in the D. And that fills the D and closes it. Now it turns out for the case of gold, this works. There's no way I expect you to be able to predict this. I'm not expecting you to rationalize it because it doesn't always work. And we're going to look at some examples where it won't work. But you're expected to know this as the proper electron configuration for gold. So that means you must memorize this configuration. Yes, you can go through this process and generate gold's configuration, but you must remember to promote the electron from the S. And this is an exception to our general rule. Well, wait a second. Gold 79 has this pattern, S squared D9. Are there any other elements like that, S squared D9, that will come close to doing what gold will do? Well, I would like you for homework to look at some examples such as the electronic configurations for silver and copper. And indeed, you will find that silver and copper can do the same thing. If you look at silver 47, if I add up the electrons and go to only 47 electrons, 10, 20, 30, 38, 48 will drop 1. That would be a D9. Silver would end here. Do I take this S electron to make 4D10 and 5S1? And the answer is, indeed, for silver, you do. If I look at the element copper, copper has atomic number 29. 10, 20, D9, 29. If I put a 9 in the D and stop there, that would be the electronic configuration for copper. Do I promote the S electron to get D10, get 4S1, 3D10? And in the case of copper, it also works. So this promotion of one S electron to give you the closed shell, the closed subshell D10, a filled subshell, works for silver, copper, and gold. If you look at a periodic table, you see these are arranged in the same column. These are members of the same elemental group. And because of similar electronic configuration, these elements have similar properties. So I must memorize that copper, silver, and gold will promote one electron from the S to give me the D10. It's in the gold case, it actually jumps the F, but that's all. Well, are these the only elements, special cases that I have to memorize? Well, indeed. Let's take a look at another element. In this case, let's take a look at the element chromium. And I believe its atomic number from the periodic table is 24. If I go along and do chromium following my diagonals, what would I predict its electronic configuration to be? 1s, 2s, 2p, 3s, 3p, 4s, 3d. And if we put in electrons, we get 2, 2, p's can hold 6, s's hold 2, p holds 6, s holds 2. I need 24. What have I got? 10, 20. So I only need 4 electrons. Okay. All right. 3d4. The D's can hold 10 electrons, but we're 1 away from 5. We're 1 away from half filling a subshell. It turns out half-filled subshells are also especially stable. Not as stable as filled subshells, but they do get an enhanced stability. If that's the case, if there's a special stability for half-filled shells, would it do the same thing as the copper, silver, and gold? That is, take 1 electron out of the S, leaving 4s1, and adding it to the 3d4 to make 3d5? Does chromium do this? And it turns out that actually chromium does. Chromium will promote an electron to get a half-filled D shell. Well, let's go down the group. Who's below chromium? Below chromium, we have molybdenum. And the atomic number of molybdenum is 42. Atomic number 42 for molybdenum. Okay, so let's start doing it. We've got 1s, 2s, 2p, 3s, 3p, 4s. Then we've got 3d, 4p, 5s. So 3d, 4p, 5s. After 5s comes 4d. Is that far enough? Let's check. The s can have 2. S can have 2. P is 6. 2. P is 6. 2 for s. D is 10. P is 6. 2 for the s. And D can have 10. Let's add that up. 2, 4, 10, 12, 18, 20, 30, 38, 48. We need 42. So 38 to get to 42, I only have to add 4. Wow, there it is. Just like this guy. 4s squared 3d4, 5s squared 4d4. I could get a half-filled shell by promoting an electron from the 5s. So should it be 5s 1, 4d 5? Does molybdenum do this promotion? And indeed, if I looked at the case of molybdenum, it does. So my list of memorization has to expand now to include copper, silver, and gold, and chromium and molybdenum. They all promote 1 electron from the s into the d's. In the case of copper, silver, and gold, it gives you 10 electrons in the d. But chromium and molybdenum will give you half-filled d's, or 5 electrons in the d. Now, when I do this problem, you notice I'm taking the time to draw the normal one first. On a quiz, if I was asked for the electronic configuration of chromium, I would write this out. I would, on scrap paper, do my diagonals, figure out this ranking, and then on the final answer, I would write 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s1, 3d5. But on scrap paper, I would have done all this to make sure I've got it right. Why did you stop at molybdenum? Let's go down. Chromium, molybdenum. Who's below molybdenum? The element is, go back to blue, tungsten. What's the atomic number of tungsten? 74. Well, if I was to replace gold, and I'll just use this, if I went through and did tungsten here, 74 would be a 4 here. Do I promote 1 electron from the 6s to get 5d5? It turns out tungsten does not. As I said, the half-filled D shell does not give you as much stabilization as a completely filled D shell. And the net effect is by the time you get down to tungsten in the periodic table, the stabilization of the D is not enough to get to below the S. And so tungsten you don't have to memorize. Just do tungsten the ordinary way. Do not promote tungsten. All right. What about some other examples? If we can promote 1 electron from the S to get a filled D, could we find an element which, say, promotes 2 electrons to give us a D? Why don't we take a look at the element palladium? Palladium. Okay, so I'm going to come down here, replace molybdenum with palladium, PD. Now, if I look on the periodic table for palladium, palladium is 46 atomic number. It means I have to put in 46 electrons. Okay, let's do some erasing. If I come along and I follow my diagonals, I'll get the 1s, the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. I fill them in, 2, 2, 6. S is 2, P is 6, S is 2, D is 10, P is 6, 2. If I add this up, what do I get? I get 10, 20, 30, 38. 4d8. Ooh. What happens if I promote 2 electrons? I get the filled shell. 5s0. 4d10. Does palladium actually promote? That is this D subshell really lower energy than the S? And the answer is yes. So now my memorization of the elements includes copper, silver, gold, and I'll write these out for you. Okay, chromium, molybdenum, and palladium. What's interesting is promoting 2 electrons is harder than, or moving 2 electrons causes energy changes that are such that the Ds might not remain low energy. And it turns out that this only holds true for palladium. What about the case of nickel? Well, nickel's one you're not going to have to memorize. If we write down nickel, who's right above the palladium, look at the case of nickel. What's the atomic number of nickel in the periodic table? Atomic number is 28. If we look at the case of nickel, following our diagonals again, generating 1s, 2s, 2p, 3s, 3p, 4s, 3d, we get 10, 20, we need 28 electrons. One could envisage, hey, I'm going to promote those 2 and make this D10. So S is 0. In actual fact, if 4s was 0, you wouldn't have to write it. I would accept a 4s 0. You could just not write it, and you could go 3p, 3d, 10. Point is, does it do this? And the answer is no. Nickel does not. It turns out that the blue normal ranking is correct. This suggests that there's a very subtle behavior about electronics in the electronic configuration, that sometimes you get this promotion, sometimes you don't. So you don't have to memorize nickel. Do nickel as normal. But I'm going to give you one last one to memorize, who is really weird. Okay, and the reason I'm going to show you this one that's different is because I want to show you that sometimes nature does not behave in a predictable fashion using our simplistic rules that we sometimes apply. And so I'm going to replace gold up here, gold 79, with platinum 78. And you should try doing this yourself for homework. Now, if I was to do platinum because it's the same gold, I'd follow my diagonals, 1s, 2s, 2p, 3s, and you can see 1s, 2s, 2p, 3s, 3p, 4s, 3d, just keep following the diagonals. 4p, 5s, then jump to 4d on the new diagonal, 5p, 6s, 4f, and d. Now, if I added in all my electrons, okay, we get 10, 20, 30, 38, 48, 56, 60, 70. I need 8 electrons. Platinum is 5d8. Okay, great. But can I promote the 2 electrons? Ooh. And get 6s0, 5d10. Well, guess what? That's wrong. And that's wrong. What actually happens? Well, what actually happens is going to be unexpected. We're actually going to get 6s1. Still have the 4f14 and 5d9. We're not even getting a filled shell here. If the D's were lower energy, why wouldn't you promote the other electron? Wouldn't filling it give you at energy stabilization? I'm afraid to understand what's going on in the case of platinum, one would have to look at the actual quantum mechanical calculations. However, we're not going to go that far. So I'm going to require you to memorize platinum as the oddball. All right. So what do you have to know if you're doing electronic configuration? The first is to be able to draw this pattern on scrap paper. Put in your diagonals and get your general ranking. You have to know how many electrons go in each subshell. And once you know how many electrons go in each subshell, you can put in the appropriate number of electrons and get your electronic configuration. The only elements you have to memorize for this: copper, silver, and gold. And I write them above each other just the way they would appear in the periodic table. That is copper, what is it, 29? Silver, 47. And gold, which is 79. I want you to also memorize chromium, 24, and molybdenum, 42. And lastly, you will also memorize palladium, which is 46, and platinum, 78. Remember, all these elements, all of them, add one electron to the D, or 2 electrons. These guys give you filled D. This guy gives you half-filled D. And platinum is the oddball out, promoting only 1 electron and not getting either filled or half-filled. Okay. What I want to do now is take us right back to the electronic configuration of nitrogen. So let's start up here with nitrogen 7 electrons. I follow my diagonals. I draw this on scrap paper. I get the 1s, the 2s, 2p. The s can have 2 electrons. I need 7. That's 4. So we put 3 in the p. This is called an electronic configuration. If you are asked for an electronic configuration, you give this on the quiz. But you could be asked for atomic energy level diagram. What's that? You may remember last lecture where we represented orbitals as lines. We represented orbitals as lines. And so we would draw something like this, and we could call it the 1s. And we would put electrons in there symbolized by arrows. The atomic energy level diagram is just that. It shows the orbitals, shows the electrons as arrows, and as you go up, it's higher energy. S only has 1 orbital. But when you get to the p, you have 3 orbitals. Now we must follow all of our rules when we're filling these orbitals. And what rules were they? Well, the first rule was the Aufbau Principle. And what did the Aufbau Principle state? The Aufbau Principle stated that you must fill, or electrons occupy, orbitals of lowest energy first. So as we start adding electrons to the bare nucleus, they'll go in the 1s first because it's lowest energy. So I start there. The next rule we follow is the Pauli Exclusion Principle. The Pauli Exclusion Principle states you cannot have more than 2 electrons in an orbital, and they must be of opposite spin. And we symbolize spin with the heads of the arrow. So I started with the 1s, filled it. Then I went up to the 2s, filled it. And now we have 3 electrons to put in the 2p. And this is where we get into trouble. How do we fill these orbitals? Neither the Aufbau Principle nor Pauli Exclusion Principle help us here. But when we are ready to go and put electrons in here, I could put 2 electrons in one orbital, opposite spin. I could put, and then add another one here for 3. I could put all 3 electrons and alternate them. 1 up, 1 down, 1 up. So alternating the spin. Or I could put 1 electron in each orbital of identical spin. Turns out Hund's rule, our third rule, helps us, or third principle, helps us determine which procedure is correct. Okay, so what that means is when we come along and put electrons in, we don't pair up first. We draw electron. Now, it doesn't matter if you draw the arrow up or down, but if you draw it up, all the others must be up. And we fill with 1 electron each orbital with identical spin before we pair up. Now, if there were 4, if we were doing oxygen 8, then we could start pairing up. So this is nitrogen. What we have here is the atomic energy level diagram for nitrogen. If on a quiz you're tasked for an atomic energy level diagram, this is what you draw. And you'd keep going up in height. I mean, if we had the next one, the 3s would be above it, and so on. You keep going up. This is an electron configuration. Make sure you read the question carefully and give the appropriate answer. Excuse me. All right. So there you have a quick summary of electron configuration and energy level diagrams. Now, before I give you a homework problem, I'd like to define one more thing. I'll just get rid of all this. And that is valence electrons, because that's going to be pertinent to our next lecture, and they're going to be important to consider. One of the approaches to understanding bonding involves the concept of valence electrons. And it goes like this. The idea is that the outermost electrons are the most highest in energy, and hence they're the most reactive electrons, and hence they are the ones that participate in bonding. So we need only consider the outermost shell of electrons. That is, if we're dealing with nitrogen, right, which has 7, we've already seen it's 1s squared, 2s squared, 2p3. The highest energy electrons are the electrons in the second shell. The electrons we only need be concerned about are the electrons in the 2 shell. The electrons in the outermost shell are referred to as the valence electrons, and so nitrogen is said to have a valence of 5. The 1s is energetically too buried to be used in reaction. Now, this is the approach that's used in one of the theories of bonding, called valence bond theory. Now, nitrogen with 5 valence electrons is represented in what is called a Lewis dot diagram. And a Lewis dot diagram involves drawing the element symbol and then just drawing 1 dot for all the valence electrons. And so this is a Lewis dot diagram for the element nitrogen. This is important because we're going to use the concept of valence electrons and diagrams like this to produce Lewis structures of molecules. And that we'll be doing in the next lecture. So there you have it. Atomic structure is important in understanding the nature of the electron around the nucleus. We can extend that to produce electronic configurations and atomic energy level diagrams for various elements of the periodic table. It was important we learned how to get the energy ranking of the subshells. And then we looked at some special case exceptions, where we had half-filled and filled subshells that were especially stable.